humans are now after 13.7 billion years. So if we look into the universe, it is in every direction, but it is just showing in one direction. If you go back in time, so if you are looking at a star farther, say you go a little bit further, say 4 billion years back, a star, some redshift 0.2 or 0.3, then you are looking at a younger time. Is that right? When universe was younger, 4 billion years back time. So what you should see, if you go back even more and say you go back in the middle of this picture, that much distance, far distance, say 8 9 light years beyond. That means you are looking at 9-10 billion years back. So what you should see that time? You should see the actual stars like that or something else. Can somebody speak? Anybody? When you look at a powerful telescope, then what you will see? You will see that time the light rays are coming from stars which are very, who will speak?
Young stars.
Very young stars. So if you go even a little bit back, means distant stars, you will actually probe that their birth. So the first stars forming here just after CMB, you can see the glow. Faster 400 million years later of CMB, about 400. CMB at 300 million years. So we have been developing telescope to observe that, and that is called the Re-Ionization Telescope or 21 centimeter telescope. Till now, with optical telescope, it's very hard to go all the way here. Means 400 million years after Big Bang, but definitely 9-10 billion years before we are seeing the stars. So that means you are seeing a star which is much younger. They are just born. So their chemical compositions, when a star is getting born or a galaxy is forming, that's the beauty in cosmology, that the further you go back, actually you are looking at the younger universe. So looking at galaxies which are being born farther away, that means you are looking at younger galaxy, you can actually see how galaxy forms. Because then you go a little bit back in distance, then you see what was the state of galaxy a little bit before. So at different distance, you are getting not only space information, but you are also getting information, evolution about in time. Is that clear? Because you are looking at younger things. Clear? Is it? Yes. Hello?
Sir?
Yeah.
Those things are over, right? Like in a sense, if a star is born, it is born. So presently, if you look at it, we see a star which is glowing, or maybe it's like a middle-aged star.
But the light ray which emerged that time, which is reaching us today, will give us a picture of the star not now. What was the state of the star 10 billion years back?
Yeah, that's correct.
Getting it? So that's the beauty. This is a little bit different than normal or photography. Here, using whatever is there, you will see. But here, you are seeing further means you are not seeing their present status. You are seeing their status 9 billion years back, because light ray takes 9 billion years. Yeah, correct?
Yeah, yes.
That is very interesting. So that's why, if you go back a little bit more, that CMB picture in this picture, that is when the hydrogen atoms first formed. We talked about it. Yeah, 13.6 electron volt below when temperature, then the photon gets released. Yeah, and the picture of that CMB sky we got today, it will be like this. I'm showing you. So this is the picture, and this is the mathematics. that this is a 3D disk from where the photons are coming to us at the center. So you are seeing a snapshot of the universe 0.38 million years after Big Bang, which is pretty old, baby universe, as I talked last time. Now, this disk, like an IMAX movie, sphere, it will only carry the light to you, as I discussed in the last class, which is 0.3, which was at 0.3 million years back. And that's why when we see their picture in WMAP telescope, you'll be amazed to see, we see this. This is the picture we see. So, these little colors are tiny fluctuations in the temperature. So reds are a little bit high temperature, blue a little bit low. But these fluctuations are 1 part in 10 to the power 5. So the mean temperature is how much? Mean temperature, which is exactly smooth, but they have a 1 part in 10 to the power 5 fluctuation. So you know what is the mean temperature we discussed, no, last time? Who can tell?
2.7 Kelvin.
2.7 Kelvin. So you will see a fluctuation 2.7 plus minus 10 to the power minus 5. And that fluctuations, it feels like a random fluctuation. This is the map we got. You can think about is the afterglow after the creation, because 0.3 million years is nothing. It is like a baby universe compared to 14 billion years. So this is like the most earliest baby universe picture. There was no galaxy, no stars, just photon got released from an atoms formed, but the photon has a temperature fluctuation. Okay. Now you'll see this thing later, maybe 9th or 10th class, last 2 class. This thing carries like a golden information when you know how to do statistics. When you know, build with the physics, the power of physics, of atomic physics, how hydrogen atom form, what was the gravitational potential that time, build with the cosmological equation. This simple statistics gives amazing information, and you will be amazed to know it gives how much was dark matter at that time in the universe. It tells how universe got created from nothing, at least to some extent. It tells that the plasma, which is hydrogen, just after it was in plasma state, just after before it formed the hydrogen atom, it was plasma state, and it tells that there will be a black body radiation with that 2.3 Kelvin, 7 Kelvin, but that is the peak of the black body radiation temperature. It will give exactly a distribution of Planck distribution. So how much will be the distribution of the photon, and that distribution is verified today. Okay, it is not only just the temperature 2.7, but it's also, and now more than that, these tiny fluctuations here are basically quantum mechanical origin. Means it came, as universe came from a point, nothing. So it came from quantum mechanical distance. These fluctuations are because of that. And from quantum mechanics, you can actually calculate the statistics of this fluctuation, and you can, in fact, probe in the beginning of the universe. So not only that, there are many more information which I will tell you later. You can get a polarization map because photons are polarized. You can get many things, and that's why, and you can tell how much dark energy is there at that time, how much dark matter is there at that time, how much baryon, means how much visible matter was that time. All these things can be found from this simple map. But we'll now not go into the detail, but just to give you an idea that this is the earliest universe we have seen. And iske pehle, if you want to probe even earlier, then photon is not possible because photon was doing random walk with the plasma because it was ionizing the electrons. So photon was not free; it was getting collision with that. So that's why photon could not travel. So that's why this picture I was showing, this one. That before that, opaque. Opaque means it's dark. There will be no light coming from there because light was not released before that. Is it clear? Yes?
Yes, sir.
Yes. So even if you have a powerful telescope, you will not be able to see it because there is no photon coming. So this is the latest from now or earliest from now, 13.7 billion years back. You can see this snapshot of the universe. Now, if you want to see before, suppose you want to see what was happening. Sorry, I have to take some phone call. Okay, suppose these are the area. What you want to see from here, then you have to do some experiment called gravitational wave experiment. So gravitational wave are the experiment which can bring you information because gravity wave can propagate in any medium without any resistance. That we will discuss later towards the end. So this is the brief history of the universe I have given you. Now let us go into the derivation of cosmology. Okay. So any questions till now? Now I'll get into the Friedman equation which we discussed last up from the metric. Okay. So any question? Yes or no? No. So what is our metric of the, sorry, this is the problem. Sometimes it just collapses. Can you see the whiteboard?
Yes, sir.
Yes, sir.
Oh. Okay. So who can tell me the matrix of the FRW matrix of the universe? Tell me minus. Who will tell me? C square.
Minus c square dt square
Yes.
plus dx square
Plus.
dx square
No. Before that there is something.
a square t
We'll write it in the spherical polar coordinate. Okay. But what is there? There is
a
a
square
factor.
t
Huh?
a square t
Hmm.
a
What is A? Who can tell?
scale factor
Scale factor of the universe. Okay. And then here,
ds
now
ds square
go into the spherical polar coordinate. Okay, because that is the best. So it is dr square by 1 minus, who can tell?
kr square
K value is 0, that we'll know it later, but right now we'll keep it. Next, spherical polar coordinate, everybody knows, no? How? We'll write, these are like normal, like Cartesian, say spherical polar transformation. What is that? R square?
R square dt pi square R square.
The square plus
sine r square sine square
D pi square.
theta d phi square
this equation you should memorize. Because without that, you cannot do anything. Clear? Yes? So now, what is the metric here? FRW metric, G mu nu as a 4 by 4 metric. Who can tell me? Somebody else? We did it all last class. What will be the term here? In the unit C equals to 1, natural unit. Okay.
Minus 1.
So this will be
Minus 1.
minus 1. And then,
A square upon 1 minus k square.
so it will be a square. Clear? For the flat universe. Yes? Rest of the term is 0. So this is your metric for special relativity. Eta mu nu, what is the metric for flat space-time? Flat space-time. That is the special relativity. What is the metric? Somebody else should tell, who have not spoken yet. Who will tell? You remember, no? So Shruti, you want to tell what is the special relativity metric in terms of this diagonal metric? How much? What is the ds square in special relativity? We talked about it. We can't hear. Somebody else who wants to tell?
Be one diagonal one matrix.
No, minus 1 for the
Minus 1, 1, 1, 1.
plus 1, plus 1, plus 1. Because the distance square is minus c square dt square plus dx I square. I goes from 1 to 3. Clear this much? Okay or no?
Yes, sir. Clear.
So other people who are not responding, slowly you have to read what I am telling, because now we'll go into a little bit more deeper level. So if you don't read, if you just come and sit in the class, after sometimes you'll be totally lost. Okay. So 2 people sent me the homework. Other people did not. I will not give you like a written homework because I will not grade it. It is for your interest only. Okay. So the derivation, have you done? Anybody has done the derivation that I gave you? Z.
Yes, sir.
Who has done? Write it down. And who has not done? Yes or no, or you could not do. So all these things are allowed. Okay. Avinas has done 80 part. Avinas has sent me the homework, and Jahang has sent me. Rest of the people, not yet. So you have to do it, because if I'll give you little homework in every class. See, cosmology is the most fascinating subject, but if you don't do homework, then first of all, online it is very hard. Okay, and then you don't know the GR, you don't have not studied special relativity long back, you studied. So you have to do the homework, otherwise you will forget everything. Okay, so the homework done by Jahang. So let me see whether I can share it with you. Jahang, you emailed me, no?
Yes, sir.
Let me see whether I have it here. Anyway, I have downloaded it, but somehow I am not finding it. Let me see. So what was the homework? Anybody knows? Those who have not done it yet. What was the homework? One is the different epoch of the universe. Another is derivation of the. Who can tell? Integral equation. From there, we wanted to solve AT, this relation between AT and the lambda. Yes, you remember? And it is not so straightforward. If you have not done it, इतना easy नहीं है. So how many of you have tried but could not do it? Yes. Please say yes, tried or did not try. So that's the thing. Today is Friday, so weekend. Rest of the people, can you do it in the weekend? So this is the answer which Jahang has sent me. So I'll not show it here. You try that. You will see that it is not so straightforward. Okay. So if you do this small thing, then it will be easy for you to do it in the exam. Okay. So shall we all do that in the weekend? Yes. Homework. Yes. Yes. Otherwise, you will not do it. Okay. Very nice. So now let us move to general relativity. Okay. That's why before moving to general relativity, I wanted to make sure that you understand all these things a little bit. So now, can you see the whiteboard? Yes. So GTR, General Theory of Relativity, Einstein, it itself is a 2-semester course, but I'll give you the basic concept and two way I will describe this so that you can get an idea. So for Newton, the gravity is a force. For Einstein, gravity is geometry. Geometry of space-time is gravity, Einstein said. So how he went from this force, first of all, nobody see the force. Everybody see the effect of the force. That apple fell. Apple was falling for so many years, but nobody could find out that there is a Newton's law. But Newton could do that. Okay, but then what is the basic idea here? The idea is very simple. If you ask Newton that a train is coming and you ask Newton that tell me where the train will go. So at t equals to 0, suppose there is a train is coming, a train is at a position x, train. And the train has this track, like a train track, and this is the next station, this is the station 1. So if you ask Newton that tell me that now it is t equals to 0, say t equals to 30 minutes from now, time, where the train will be. What Newton will do? Newton will solve the differential equation. Yes, right? Newton will calculate the force of the engine and this, and which direction, then friction. It's a very tough problem because every position in the railway track there will be a friction, there will be a reaction, there will be a friction from the side. So that Newton will do and tell you that how the things will work. But Einstein's will tell the train will just follow this track because I know the geometry, so train cannot go somewhere else. Is it getting clear? Yes? Because once you know the track and train cannot go beyond the track if there is no accident, the train has to follow the track and then you know that where the train will be. But of course, the time part, that depends on the equation. But the basic idea is Einstein will not worry about force in each point, that which direction the effective force is coming, and then train will go, and when the bending is happening, then maybe this side more force is there. That's why Einstein says it has to bend like this. So this is the philosophical idea that if you know the track, you don't need to know the exact solution of the complicated force. So in the same way, this is say sun and this is earth. Newton solved the Earth equation by solving the planetary equation, which is basically nothing but Newton's law in the inverse square force. Right? Yes? Say something or say yes. Yes? You know that.
Yes, sir.
Yes, sir.
You know that centripetal force, Kepler's force, you know that. No, you have done it. Yes?
Yes, sir.
But what Einstein says, so Newton did a very complicated geometry and then Newton find out the planetary motion. Planetary motion. By solving the Newton's law, which is the, I have told you, in the left side. But what Einstein did is a little bit different. Einstein, the idea is, he said that when you put sun here, the space curved. Because space-time is not nothing. Though we can only feel the nothing around your body right now, the space. But in physics, the more you go deeper, either in general relativity or in particle physics, you will see nothing is not nothing. In fact, nothing is everything. So what you cannot see, it can bend. So it's a complicated geometry. And once the space bent, now if you put Earth, and if you give it a initial velocity v at kick, then you know that to keep it that position, the motorcycle in a mela or in a fair, it has to move, because if it does not move, it will collapse onto the sun, right? Yes.
Yes, sir.
So in a curved geometry, you have to move, otherwise you will collapse into the center. And that's the idea that Einstein said geometry is curved. So even if Earth is moving like that, it is because there is a curve. And now if you don't give a initial velocity, just keep it, then it will just follow the curvature. It will roll off. And that rolling off, I will call it as the attraction of gravity. So it's nothing but, suppose you have a bed sheet, and if you put suppose this is your bed sheet. If bed sheet is straightened up, then if you put a particle here, it will remain still. But suppose you put a very strong iron ball in the bed sheet, then bed sheet will curve. And then you put the particle, you will see particle rolls up. So you can clearly see that if you change the geometry, then there is a force generated, and that is geometry is equivalent to force. Is it getting clear? Yes?
Yes, sir.
Any question? It's very simple. If you have any question, you can tell me. Okay? So this bending of space is a pictorial representation, because you can see the bending of something, some bed sheet or paper, but you cannot see the bending of nothing. First of all, it is empty space. You cannot. It is not like a fluid. When I say it is not nothing, you are immediately think, oh, is it a fluid? No, it is not even a fluid. It is nothing. No, absence of every matter is space. But still it is not nothing. It can bend and it can twist. So that's why Einstein was a genius, that he could sense which is beyond the eyes, which is pervading the whole universe, empty space, but it can turn and twist. Okay? So the basic idea of GR, if you are falling asleep, so and if you want a little bit of entertainment, so then I will show you a video. Let me see that if I get it, if I have it here. I have in this computer. Otherwise, I will send you later. Yes, I think I am getting it. Yes. So let me share this video with you. Then you know what is from Newton's to Einstein. It's a genius. Can you see the screen? Full screen you can see? Now?
Yes, sir. Easy one.
And long before Einstein, the quest for unification began with the most famous accident in the history of science.
As the story goes, one day in 1665, a young man was sitting under a tree when all of a sudden he saw an apple fall from above. And with the fall of that apple, Isaac Newton revolutionized our picture of the universe.
In an audacious proposal for his time, Newton proclaimed that the force pulling apples to the ground and the force keeping the moon in orbit around the Earth were actually one and the same. In one fell swoop, Newton unified the heavens and the Earth in a single theory he called gravity. After nearly 10 years of racking his brain, he found the answer in a new kind of unification.
Einstein came to think of the three dimensions of space and the single dimension of time as bound together in a single fabric of space-time. It was his hope that by understanding the geometry of this four-dimensional fabric of space-time, that he could simply talk about things moving along surfaces in this space-time fabric.
Like the surface of a trampoline, this unified fabric is warped and stretched by heavy objects like planets and stars. And it's this warping or curving of space-time that creates what we feel as gravity.
A planet like the Earth is kept in orbit not because the sun reaches out and instantaneously grabs hold of it, as in Newton's theory, but simply because it follows curves in the spatial fabric caused by the sun's presence. So, with this new understanding of gravity, let's rerun the cosmic catastrophe. Let's see what happens now if the sun disappears.
So now, what we are going to do, there is a hypothetical test between Newton's and general relativity, Newton's theory, and which one is true. According to Newton, if there is no geometry involved, just gravity is a force. So the basic assumptions of Newton was the force is instantaneous. Means if you put Earth and bring sun in the middle, immediately Earth will feel gravity, and that's what we all thought. But that is not the case. So how do we know that that is not the case? And in fact, that got the Nobel Prize 2-3 years back. That if it is like an ocean, the space is like an ocean, but of course not made of nothing. And when sun comes in, it twists the space, as you have seen. Now suppose sun disappear one day. You know that sun is moving through our Milky Way galaxy like a horse, up and down, yet moving around a supermassive black hole, bypassing many stars. So there are 500 billion stars in Milky Way. Any star can collide with any star any day, but of course the chances are very less. That's why we are moving safe for last 5-6 billion years. So not a problem. But in principle, it can disappear, or maybe say one day sun is out of fuel of Chandrasekhar calculation, and it will become a white dwarf because its mass is less than 1.4 solar mass. So then what will happen? Immediately sun disappear, Earth will not thrown away into emptiness immediately. But according to Newton, if sun disappears immediately, now the Earth will also be thrown into the space, because there will be no F by R, 1 by R squared force immediately. But that is not the case. Let's see.
The
The gravitational disturbance that results will form a wave that travels across the spatial fabric in much the same way that a pebble dropped into a pond makes ripples that travel across.
So still, and the speed of these waves, Einstein calculated, that I'll give you as a homework, if I get some time, because in one cosmology lecture it's very hard to do gravity wave. But there is a wave equation, and you get the speed of this gravity wave ripples is actually same as speed of light. So even if sun disappear, how long this gravity wave will take to reach Earth? Who can tell?
8 minutes.
8 minutes. So you will still worry about corona for 8 minutes, because though sun has disappeared, but you will not know it, because it takes 8 minutes. So in the same way, the light which has the stars we are seeing now, billion years back, maybe they have died. But when the light is reaching us from billion light years back, we are seeing them that star is there. As some of you asked the question, sir, if the star is there, it is there. But no, cosmology is different. Here also, you are looking everything which is already in the past 8 minutes. So now,
Surface of the water. So we wouldn't feel a change in our
now
orbit around the
Earth will
sun
vanish.
until this wave reached the Earth. What's more, Einstein calculated that these ripples of gravity travel at exactly the speed of light.
And so, with this new approach, Einstein resolved the conflict with Newton over how fast gravity travels. And more than that, Einstein gave the world a new picture for what the force of gravity actually is. Its warps and curves in the fabric of space and time.
Einstein called this new picture of gravity general relativity. And within a few short years,
Within a few short years, he became a household name. So you enjoyed the video? You can give some thumbs up. This is the clear picture of feeling about this. Okay? So if you have enjoyed, then you should turn on the video. No? We should see everybody. I'm also turning on in every class. Before we get into mathematics, let's all turn on the video. Okay? So everybody is doing good? Yes? Yes. Srivardhani, we haven't seen you yet. Other people we have seen. Okay? Okay. Very nice. Where is... Okay. So you are enjoying till now? Yes? Yes? So anybody has done GR course here before? No? Okay. So now we'll get into the GR. So Srivardhani, you can turn on the video? Okay. Some technical issue. Next time. Okay? We haven't seen you yet. Okay. In class room, you cannot avoid. No, everybody see each other. Only in Zoom we can avoid. Okay, but it's good to be ready with the video so that you are attentive like a classroom. Okay, otherwise I am speaking here, video is going, and there is no dearth of WhatsApp message nowadays. You know that, no? And so many social media, you can easily move back into somewhere. Okay, very nice. Now you can switch off the video. Yes. Okay. So now this philosophy of Einstein looks very interesting, but it was extremely difficult for Einstein to give it an equation. And he took few years, he went to some mathematician, because how to describe the curvature of space and time into mathematics is not easy. For that, he learned Riemann geometry, how to define a curvature, and he learned tensor calculus. And then with that, he could come up with the equation, Einstein's general relativity equation. You can see the blackboard, whiteboard.
Yes, sir.
Yes.
So left hand side is the geometry, and right hand side is what you put. You can put mass, you can put energy, or you can, mass means massive object, or you can put smooth density. So depending on that, so this side is actually called trace energy tensor. So there is something called T mu nu. You have heard about it. Yes, in elasticity or in some. This basically for massive object like Schwarzschild, like black hole, point object, it's different. For a fluid, it is different. But for universe, we should treat the whole universe as fluid. You remember that? Yes? Yes? That universe is a fluid, homogeneous and isotropic fluid from large distance. Yes or no?
Yes, sir.
Yes, sir.
This is your homework now again. This we don't have time to do. For a homogeneous and my handwriting in this whiteboard is very hard, and isotropic fluid, FLUID, fluid. This is your homework. It takes the shape rho, means in a matter density, means smooth density of the universe, minus P, P is the pressure of the fluid, and minus P. This is your homework. Rest of the elements of the matrix are 0. It's a diagonal matrix. So now you know that here mass and energy are equivalent because E equals to mc square. So it doesn't matter whether you put some energy, that will also bend space. Whether you put mass, that will also bend space. Because mass and energy are same. Or you put smooth density of the universe, it will also bend space. Now what is the left side? We don't have time to derive in this class all the mathematics. That itself is 8 class, 7, 8 class. But I'll tell you, the geometry of space-time is G mu nu. And it is R mu nu minus half G mu nu times R. This R is called Ricci scalar, and this is this R you don't need to know. This is called Einstein's tensor. Tensor of the space. So you can see this one, both this one. If you know how to, there are a lot of software because it's a very complicated equation, which if you put the metric G mu nu, it will calculate the whole G mu nu. So basically G mu nu is nothing but a function of the metric G mu nu. So it's nothing but the metric. So if you know how the distance measured in the space-time or from other way, like we calculated the FRW metric by homogeneous and isotropic universe AT, and we from our Euclidean space-time we calculated how the coordinate space is expanding. So if you calculate that for this, and this R mu nu have double derivative. So just to give you an idea now, I'll share something. So let me see. Can you see the note? Yes?
Yes, sir.
Okay. So this is the equation. R mu nu minus half G mu nu R. This Ricci tensor and Ricci scalar, they are all function of G mu nu. So if you put it in a computer or a mathematical code, it will do a lot of calculations and find out that calculations are the geometrical calculation which Einstein learned from Riemann, a mathematician. Lot of double derivative, covariant derivative, all these things. But ultimately, you see the equations are very similar. This has double derivative, the left hand side. This has double derivative, left hand side. And right hand side is T mu nu. T mu nu has rho. So you can see Newton's gravity. These also have double derivative, grad square phi, and right side has 4 pi 0. You know this equation, right? Grad square phi is 4 pi 0. Yes?
Yes, sir.
Yes, sir.
Poison.
Yes, sir.
What is this equation?
Poison. Poison equation.
I'll show you. This is similar for electromagnetism for gravity, yes, and phi is the gravitational potential, yes. For electromagnetic, it is D'Alembertian apparatus times A mu is 4 pi by C J mu. J mu is the current. So you can see that A mu is equivalent to G mu nu. Now we have a double tensor in GR, and grad square A mu nu is equivalent to G mu nu, Einstein tensor. So left hand side. And T mu nu is T mu nu. So it has also the similarity of the, it also follows the continuity equation of classical mechanics. T mu nu is conserved, so grad mu T mu nu is conserved. So if you do that classical that equation, and as I was telling you that T mu nu is basically originally given by this will be your homework. In Landau Lisids or any Google, you can search for stress energy tensor for a fluid. Perfect fluid is given by this. It can be done from special relativity, and u nu is basically like that. Ui is expressed component as 0 because it's a co-moving frame. You are moving with that because we are moving with the universe. We are on the balloon, and u naught is 1. So this is your homework. Once you do that, then your continuity equation grad mu T mu nu gives you this equation. Delta rho A cube, d of delta rho A cube is equal to minus P d A cube. See, this A cube can be thought of as the volume, some constant time volume, because A is the scale factor and it is stretching in every direction. So A cube is proportional to volume time, a constant. And rho A cube, left hand side, d of rho A cube, rho is the density and A cube is the volume. So density times rho is the total energy. So change in total energy is P dV. It is the work done. So that's what the thermodynamics is coming back. But here we did not use thermodynamics. We just used the continuity equation of classical mechanics. That is your homework. If you do T mu nu, grad mu, T mu nu, this will be also your homework. Show that it gives you this equation. So you can search in Google, there will be a lot of cosmology notes and all this thing. You have to do these calculations, okay? PdV. So it is basically the change of energy of within a energy density, within a volume is minus PdV, the work done by the system. So now you have to take pen and paper. I have something for you now. So let us write down this. I have already, I'll go into the Einstein's equation a little bit later in detail, but just this one, grad mu T mu nu 0 gives you d of rho A cube. Rho is the energy density. A cube is the volume, so total energy is minus P dV. dV is basically, again, dV is d of A cube. There is a constant term, I am cutting down because that constant term will cut down from both sides. P is the pressure. So now, one thing you will see before okay, let's do it now. So for matter, so now universe is homogeneous and isotropic, homogeneous. So it has different component. Later we'll come to know, but they are defined by their pressure. So if pressure equals to 0, we call them matter. If pressure equals to 1/3 times rho, means you have seen the kinetic theory of gas. This 1/3 factor, rho c squared comes, so they becomes gas. So in universe, photon is a gas because it's a homogeneous universe. Photon is a gas. Light particle, there is another light particle which can be treated as gas, is neutrino. Okay, and there is something which we'll take care of later. It's called cosmological constant. It's P equals to minus rho. It's a negative. Later we'll tell. It's called cosmological constant. Einstein cosmological constant. So now, here you can see that different state of matter is, this one is very important, so everybody should look into it. I am now defining a new quantity. It's called P equals to W times rho, and W is called equation of state. Mean what state the matter is. If it is in matter state or dark matter state, P equals to 0. Why P equals to 0? For example, if you have an iron balls here, iron ball made up of iron. Now suppose there is a small layer where the iron ball is content with some plastic layer. If you puncture this plastic, irons are very solid. Iron ball is made of solid iron ball. It will not come out as a particle. But if it was a gas, if you puncture the plastic, gas will come out like a gas balloon, right? Yes?
Yes, sir.
Yes, sir.
That means the iron does not have pressure. That's why heavy matter does not have pressure. But the gas has pressure. So photon has pressure. Relativistic particles has pressure. That will diffuse into the space if you puncture the boundary. But that's why matter P equals to 0. Gas, it is 1/3 times rho. It has a positive pressure. Cosmological constant has a negative pressure. It's a very interesting. We'll see, look into it later. So now take pen and paper. This is your turn now. You tell me for matter, solve this differential equation and find out how rho goes as a function of scale factor A. Can you do it now? It's a 2 minutes job. Okay? Do it. And then whoever is done, tell me the answer. Find out rho as it's a class 12 differential equation.
Sir, 1 by A cube.
1 by
A cube.
other people. I want to see when everybody get it done. Other people who has done it till now? Who said? You give me the thumbs up. Who did it? 1 by A cube. Okay, Jahan did it. Other people. Please solve. If you cannot, then we'll wait for you. Who else? Okay, Ravi is done. Jahang is done. Other people, all of you are doing. Shruti, all of you do and tell me your answer. Shivardhani, Shruti, Priyanka, everybody on Priyanka. Once you are done, say unmute and say yes, done. How much you got?
Yes, so 1 by AQ.
1 by AQ. Who got it? Avinash. Yeah?
Yes.
Other people, you have to just take the multiplication rule of product rule of calculus, side change, do the dA one side and d rho another side and integrate. Gauri Shankar is done. Very nice. Priyanka, Arpita, Shruti. Shruti is done. How much you got? 1 by AQ. Okay. Srivardhini also got 1 by AQ. Priyanka, Arpita. Okay, I hope you can do that. It's easy. 1 by AQ. Arpita also got it. Priyanka also got it. So in case if you have not, definitely you have to do it at home. It's very easy. It's class 12. Okay. So now, if you do the same calculation for, let me take some different color. If you do it for gas or radiation, actually it is radiation, it is not gas, because in cosmology the gases sometimes are very less pressure, because photon and neutrino, they have much more pressure because they are relativistic, because E equals to m square c square, sorry, m square c to the power 4, no? Plus p square c square. You know this? Yes?
Yes, sir.
Yes, sir.
Photon, what is the m? Who can tell?
0.
0, sir.
So, whole thing is momentum. So, momentum, whole energy is coming from velocity, momentum. So, that's why they are much more kinetic energy is very. This is the kinetic energy part. This is the rest energy part. So, kinetic energy Ke is much higher than mc square. Then you are called radiation in cosmology. So if you do it for radiation, you will get rho A as 1 by a to the power 4. This is your homework also. Okay? And if you do it for cosmological constant, then for matter ho gaya, for radiation ho gaya, for lambda, lambda means cosmological constant, rho lambda, you will find it constant. You have to solve the same equation. put P equals to minus rho and do it, and then you will find it is constant. So 1, and the matter goes as, here I am using the same color, sorry, but not same, 1 by A cube. And it makes sense because the matter density falls like 1 by volume. Cosmological constant density, even if you expand the balloon, as it is the energy of the vacuum, we will later come to know, it is the energy of the emptiness. It doesn't matter, the energy density remains constant, whether you stretch the space or increase the volume, because it is not coming from something, it is coming from nothing. Later we'll take. But can you tell me why this radiation density goes faster, dilutes faster? A is basically scale factor. And as the universe is getting older, scale factor is increasing or decreasing? Who can tell?
It's increasing.
Huh?
It's increasing.
Decreasing?
Increasing, sir.
Increasing, yes. So that's why the energy density dilutes, because the volume is increasing, yes? But you will see energy density for radiation dilutes faster than matter. Why it does not go like 1 by A cube? Why it goes as 1 by A to the power 4 intuitively? Why it is faster? So it means what? It means like this. It means something very interesting. It means if you have a volume, it's A cube, it has some energy density of photon, rho photon, sorry, neutrino or photon, similar, photon. Now volume becomes 2 times in every direction. It becomes bigger because of the expansion of the universe, okay? So it becomes 2A here, 2A here, and 2A here. So what is the new volume now? 2A cube. So now suppose there is some photon particle here, number of photon particles, n particles. Each photon has a energy density, rho, the total, sorry, n particles. So n by v is my number density times, so rho, let me take it here. So rho is n by v, it is called small n, number density times the energy of each particle. What is the energy of each particle? Of photon?
H nu.
H, very nice. H c by lambda. Is it clear?
Yes.
Number density, total number n, but if it is for, this is for photon or radiation. For matter, it is n number of, say there are n matter particle divided by v, same. What is the energy for each particle? For matter?
MC.
Very nice. mc square. Because in cosmology, the total energy in the right hand side, which goes into the Einstein's equation, very important, mc square. So now you can see, can you tell me now that for here, for matter, you can see that if volume is A cube. So that's why matter goes as 1 by A cube. But here radiation goes faster than volume, it dilutes faster. So if it becomes 2A cube, means 8 times, then radiation energy density, rho photon final will be actually not 1 by 8 times, actually it is 1 by 16 times the rho photon initial. But rho matter final, is 1 by how much time? If the volume become 2, 2, 2 every direction?
8.
8 times rho matter initial. Is it clear? Because one goes as volume 1 by a cube, another goes as 1 by a to the power 4. Is it clear for everybody?
Yes, sir.
Yes.
So now you tell me why. Now I am giving you hint. Suddenly, because it doesn't mean that what is going wrong. Why for photon also can be treated as a particle? Then why it is picking up another extra factor 1 by a to the power 4 instead of a cube?
Because
Bolo?
because of the lambda, it's redshift.
Very nice. See, photons energy for each particle also has a lambda here. Lambda means it's a wavelength. And if space stretches, lambda will also become stretched 2 times lambda. Isn't it? Because if space stretches 2 times, lambda will also become 2 lambda. We have thought of, that was the whole idea about redshift. Why the lambda was redshifted? You derived because the space was stretching. Isn't it?
Yes, sir.
So that's the reason you pick up another factor of A, because lambda also will proportional to A and volume is proportional to A cube, and that's why it goes as 1 by A. So now you are thinking, does that violate the energy? Because where this energy going? Because here you can match the energy because it's just the number density, total energy is conserved because N is conserved, only V is increasing, that's why matter density is 1 by A cube. But here, total energy, if you now calculate, it will be how much? It will be V times rho for radiation, final. V is 8 A cube and rho is 1 by 16 in the rho final. Sorry, V is 8 times V initial and rho is 1, rho rad is, okay, let me write it nicely. What I am going to do now, the energy conservation. Is it highlighted or not? So what is the E initial for radiation? Can you tell me in a box? Say I have this I have this A cube is the volume. So what is the total energy?
Low AQ.
Sorry, I have N particles, that's it. So it's N, it is the total energy. Clear? N photon with each energy Hc by lambda, that is the total energy, right? Clear or?
Yes, sir.
Yes. What is the final energy? So the final energy, oh sorry, right now like that we cannot do that. Let me do like that. Sorry. What I am saying is here, rho initial rho and rho final, it's like this. Here you can see it is rho final is 1 by 8 times, but the volume has also become how much time? For matter. 8 times the initial volume, isn't it?
Yes, sir.
So the total energy is, if you multiply by both sides, the V final, it will be 8 times V initial, 8 get cancelled, so it will be rho initial, V initial, right?
Yes, sir.
Shall I tell it again? I want to see the final energy density, whether a total energy, whether it's constant. So I have to multiply, sorry, I have to multiply it with V final. And what is V final is 8 times V initial, right? And 8 got cancelled. So V final, rho final is V initial, rho initial. So energy is conserved for matter, right?
Yes.
Yes, sir.
But for if you do the same thing for radiation, here multiply with V and here multiply with V, you get a 8 factor here, but there will be a half of rho initial. Getting it? It will not match.
Yes.
So does that mean that energy is violated? Who can give me the answer? You got the question, or shall I repeat it? How many of you got the question? It is clear, no?
Can you repeat once?
Ah, so that's right. So I want to check this, that I know that rho, I got my rho final, rho how it goes. Rho goes as 1 by volume cube. So I am taking an example where A becomes 2A. Universe has expanded 2 times. So it will be 1 by 8 times rho initial. Because that's what I have found out. You have found out that it goes as 1 by A cube to the power rho. So जो पहले वाला rho था, what was the beginning, it will be 1 by 8 times because volume has become 2A, 2A, 2A. Is it clear?
Yes, sir.
Yes, sir.
Now I want to see the total energy. So rho times volume, V final, is the total energy. Yes?
Yes, sir.
I multiply here also V final. And what is V final? It is 8 times V initial, isn't it?
Yes, sir.
So, got cancelled. So V final, rho final means total energy, volume times rho is V initial, rho initial. That means energy is conserved. Clear for matter?
Yes, sir.
But if I do the same thing for radiation, it goes as 1 by 16 that I have derived. 16 times rho radiation initial, because it goes as 1 by a to the power 4, right?
Yes, sir.
Now I want to do the same thing. I want to do the V, this is final, okay. V final. Now here it will be then 8 times V initial. V initial. So how much it will be?
Half of rho initial, V initial.
So that means there is a garbage, rho initial. So where it is not conserved the energy, it half ho gaya by expanding. So where is the energy going? The total energy should be conserved, rho times V. Now the question is clear. Yes?
Yes, sir.
Yes, sir.
Yes, sir.
So who can give the answer?
So that for photons, there is not only density, there is pressure also now in energy momentum tensor. In energy momentum tensor, the
So,
energy density is stored in not
so
only
you
density,
remember, yes, I
in form
got it.
of pressure also.
So other people ke liye, I am telling it. You remember that energy is only conserved in from thermodynamics when there is no external. You remember this?
Yes, sir.
Yes, sir.
But as I just says, d of rho a cube, this is the equation, minus pressure d a cube. From solving this only you got this solution, no? Isn't it?
Yes.
But pressure is 0 for radiation or not?
Yes, sir.
Not 0. So the
It's
work
1/3.
dw is not 0. But for matter it is 0. Pressure is 0. That's why d of rho a cube is conserved. So now it is your homework. Find out the mismatch, calculate the work done for radiation, and you will see that you now conserve the energy. So half we were getting, half energy was missing, that actually gone into the work done. Clear?
Yes, sir.
Yes. So this is the whole idea. So now I'll do one final thing, then we are done. So let us plot as a function of log a.
Sir,
Yes, bolo.
so this work done is going into the expansion of universe.
Yes, it is done by the space
Oh, okay, sir.
on the fluid. Okay,
Okay, sir.
because fluid has a pressure and space is expanding it, so that fluid has an attractive repulsive pressure. That's why it's a negative work done. Okay,
Okay, sir.
work done means you will match it because half was missing. That's why you have done negative work done. So that's why it's just a matter of sign which direction you take. You know that in work done has a different sign when you do it from inside or outside. Yes, yeah.
Yes, sir.
So you match it. So now we are almost done. I'm plotting now the different energy component of the universe. So 1 by matter, how it will go in log scale, how does it look? Can somebody tell me? It will look like a curve, or because it's rho I goes as 1 by a cube. So I'm plotting this. Rho matter is rho m0, some constant by a cube. Rho radiation is rho radiation 0 by a to the power 4, and rho lambda is rho lambda naught. It does not change, it's constant. That is your homework, you have to do it. This happens for w equals to minus 1, means p equals to minus rho. So if I plot it, how it will look?
Line with slope -3.
Very nice, sorry. This is the problem. I got it. This is not I am doing the homework, actually. It's a straight line with a slope -3. Clear? Yes?
Yes.
Yes, sir.
Now if I draw radiation, how it will be steeper or flatter?
It will be steeper.
Deeper, because it goes as 1 by
Minus.
-4 log factor -4. And if I plot, let me take it a little bit back. This is a straight line. I am drawing it in a whiteboard in a pad. I don't have an iPad, so that's why the accuracy is very low. And then if I do it for cosmological constant, it is a constant. This is rho lambda, this is rho matter, and this is rho radiation. Clear?
Yes, sir.
Now we stay at present time. This is from observation. We know that our position in the universe right now, a equals to 1. So this is an axis where a equals to 1 means log a will be 0. So we have shifted the axis, but this is the present epoch. Present time. This line. So now what is maximum? Who is dominating right now? You can see.
Lambda.
Huh?
Lambda.
Cosmological constant.
Isn't it rho lambda? It is the maximum. After that, it is matter, and radiation is सबसे कम. Is it clear?
Yes, sir.
So we know that in our present day universe, if it is a cosmic cake, cosmological constant is 70%. Cc, the dark energy. We'll talk about it later. And the matter is rest around 30%. Radiation is almost gone. You can see its log scale is very low. So radiation is actually now 10 to the power minus 4 times. So in this case, 10 to the power minus 4 times means 0.00%, double digit ke baad, 0.001%, something like that. But rest is matter. This part is matter. Is 30%, but out of the matter, only this part is visible matter, that is 4%. But we don't distinguish between matter and dark matter for this equation. All goes as 1 by a cube, but later we'll come to know. And rest of the matter is 26%, is called DM, dark matter. So 26% is dark matter, 70% is dark energy, which I'll talk it next class, and only 4% is all the billions of galaxy cluster, what we have seen or yet to be seen. Our visible, beautiful, infinite stars, galaxies, galactic clusters, supernova, black hole, everything is 4%. And at present, we have absolutely no idea about 96% of the universe. We only know 4% pretty much. So this is the present situation of the universe, and we are searching hard to find out. I work on dark matter, this part, 26%. Also little bit on dark energy. Ravi, my PhD student who is doing this course, he also works on that to understand what it is. So now you can see today, radiation is negligible, 10 to the power minus 4. But if you go back, there will be a time when radiation becomes the highest, right? In the past. This is the past.
Yes, sir.
A smaller means in the past. A larger means in the present, as it is the present. This time onwards back, that's why it is called Big Bang cosmology, because it was all radiation. So universe had these 3 phases. That is the last statement for today's class. One is a radiation dominated era. That will be from here to here. Then there will be matter dominated era, when matter was dominating, and then this is dark energy dominated era. So matter dominated era is MDE, matter dominated era. Sorry, फिर भी गड़बड़ हो गया. MDE, and this one is dark energy dominated, DDE, dark energy dominated era. Our universe was very hot in early time, left side. Then matter dominated era, when galaxy formed. And then at present time, we will see that suddenly dark energy or cosmological constant has taken over the universe, 70%, and it is driving the space in a very crazy way that we will discuss next week. And the discovery of this dark energy got Nobel Prize already. And this dark energy makes the space like an accelerate. So if it continues for another few billion years, every galaxy will move away from each other because of its super expansion, accelerated expansion. And few billions years later, if some astronomers watch the sky, you'll not be able to see anything other than Milky Way. So no galaxy, other things, all the things will be stretched away into the empty space because of the dark energy, and that we will see in the next class. Okay, clear? Yes?
Yes, sir.
Good. So
Yes,
it
sir.
was okay. Yes. It was, see, mathematics are very easy. I am just doing different, but the concepts here are a little bit tough. Okay, that's why you have to be okay. If you have any questions, you can ask me next class. Prepare your question. I love questions. When I was teaching in USA, I didn't used to give chocolate in every class. Now I cannot give chocolate because we are in Zoom. But I used to give chocolate to people, not for giving right answer, but for asking questions. It can be stupid questions, can be. You will see later when you go into the physics research, answer doesn't matter. What matters is if you can ask the right question. Okay? Yes? Yes? That is true for life also, actually. If you can ask the right question, that what do I really want? There was recently an article by some CEO. He said that just ask this question, that is my life goal is mine or it is somebody else's has put on me. Getting it? If your life goals is yours, you will definitely move in that direction. Okay? That's why physics also the same. Right question asking can make you answer, find the reality. In life also asking right question. What do I really want? If you can answer this question, then you will do good what you want. Okay, great. Okay, so next class we'll solve the scale factor, acceleration of the universe, and much more. Okay, and then slowly, and next class also we'll tell you how the dark energy was discovered and got the Nobel Prize. Okay, and that will be the fourth class, and then slowly we'll go into the early universe. We're using some thermodynamics, and then finally we'll do some little bit complicated. Okay, not so complicated. It is called the structure formation. Means starting from nothing, how come you produce so many things? That also you can do it by differential equation. That is the last 1 or 2 class. Okay, enjoying? Okay, good. So see you on Friday. Yes, Shruti, Friday. Yes. Is it Friday? Next class?
Yes, sir. Yes, sir.
3:30, no?
Yes, sir.
Okay, good.